Okay, so we are on Tabular Domain 3. And in this particular domain, this is one of my favorite ones. Really what we're going to be looking at here is approximating rates of change. And you guys are going to love just how easy this is. Approximating rates of change and also interpreting rates of change is the other one. That is something that we have been practicing over the last couple of weeks too. So I love these problems. They're basically free points, and the subpaths are actually not that much different from each other. They don't really go up that much in difficulty. It's really just the same pattern over and over and over with relatively few modifications to it. So once you see it on this year's AP test, you'll be pretty set for it if you practice these. Yeah, it's pretty easy to tell. All right, so let's take a look. We got Joanna here again. Joanna's jogging along a straight path. We've got time here on the x. We've got velocity here on the y. It's differentiable function v. Okay, meters per minute on the velocity and minutes on the time. And then what we're doing here is we're taking a look at part A. Remember that there is no calculator on this problem. So we want to use the data in the calculator to estimate the value of v prime of 16. So here's how all of these go. V prime of 16 is a derivative. That basically is a slope. You know that. But we don't actually have an equation. We don't have a function to derive for v. That's why this is asking us to estimate the value of v prime of 16. What we're going to do is estimate this value by using the table. We're going to estimate the slope at 16 by looking at the slope between 2 points around t equals 16. And here's how we do that. So the slope at 16, we can use these two particular points to estimate that slope because these data points contain in the middle of them t equals 16. So what we're going to do is we're going to set up what's called a difference quotient, or in other words, f of b minus f of a over b minus a. We're going to take the last velocity, which is 240. We're going to subtract the initial velocity, which is 200, basically f of b minus f of a, over b, 20 minus 12. This is basically the algebra slope, y2 minus y1 over x2 minus x1. Again, we can't actually do the calculus with v because we don't have a function. We can't take the derivative, but we can estimate what it would be by looking at the slope around t equals 16 instead. All right, so let's calculate what this is going to end up being. So 240 minus 200 is 40, and that's 40 meters per minute, divided by 20 minus 12 is 8, and that's 8 minutes. So all told, this would end up being 40 over 8 meters per minute, or meters per minute squared. And yeah, there we go. That's pretty much it. It's just finding the slope between 2 points and then making sure you've got the right units. And then you're pretty much good. Okay. Try the next few, and again, be sure to check your answers by just Google searching the AP Calculus, the year of the problem, and then solutions, and you should be able to find that. Take a look at the points that they give, the rubric, and if you got any questions, email me or find me. Okay. Once you're ready to take a look at subpath B, you can try it yourself, or if you've got a question on the first one, then you can take a look at the next walkthrough. All right, so in this one, AP 2018A, we've got the height of a tree at time t, given by a twice differentiable function h, and then h is measured in meters and t is measured in years, and then selected values of h are given in this table right here. We're going to be taking a look at part A, where we're being asked to estimate h prime of 6. So let's write that down. Let's estimate h prime of 6. So this is going to be using the same method that we did last time. We know that h prime of 6 is basically a slope, but we can't find the exact value because we don't actually have a function. So we need to find the slope around t equals 6 instead. And then what's important about this problem, what makes it one level of difficulty up from the other group, is that we're asked to interpret the meaning of h prime of 6 in the context of the problem. So let's find h prime of 6 first real quick, and then we'll interpret its meaning. So to find h prime of 6, we're going to use the points that occur around t equals 6, and that would be up there. So we're going to do, again, f of b minus f of a, so that would be 11 minus 6, or y2 minus y1, over, and that's 7 minus 5. So this would end up being 5 divided by 2, which is 2.5. And then the units on this, if you take a look, the units on the top half of this is meters. The units on the bottom half is years. So the units on this, 2.5, is meters per year. And the interpretation for this is that this is a rate of change, or the rate of change, or supposed to be the rate of change at a certain time, 6. So what we'll say here is that this, h prime of 6, is the rate at which the tree is growing at time t equals 6. There we go. It's important to include not only the calculation, but also the interpretation with the correct units as well. Those are all 3 parts of this particular question. All right, try some of the other ones. Okay, welcome back. So in this last subpath, part C, we were asked some more difficult questions about rates of change and interpreting rates of change, and that's just what we will do. So in part D here in 2013, let's first look at the context. It says hot water is dripping through a coffee maker, filling a large cup with coffee. The amount of coffee in the cup from 0 to 6 is given by differentiable function c. And then we see values of c up in the table above right here. Maybe you've worked with this problem before in the other questions. Okay, so the amount of coffee in the cup is modeled by this particular function. Oops, p of t equals that. So this is different from the table. This is just a model. And this question doesn't apply to the other ones. This is just only in part D. So using this model, okay, find the rate. Ooh, the rate at which the amount of coffee in the cup is changing. So first off, what does this model do? Does this model model the rate already? No, this model only models the amount of coffee. So in order to find the rate at which the amount of coffee is changing, what I will need to do is take the derivative of this particular function b. So let's rewrite b. So I have something bigger to look at. 16 minus 16e to the negative 0.4t. And what we're going to do is find what b prime of t would be. So b prime of t, the 16 right here will get destroyed. And then when I take the derivative of this part, I'm going to use the chain rule. The derivative of the inside is negative 0.4. And then the negative 16 just stays put. And then the derivative of e to the something is just e to the something again. This is the same pattern as if you were deriving y equals e to the 5x. The derivative of that would be 5e to the 5x. And that wouldn't really change. If I were to make a different problem and put, like, I don't know, 3e to the 5x, that derivative would end up being 15e to the 5x. The 3 and the 5 would just multiply together. And that's what's happening with the negative 0.4 and the negative 16. This is a no calculator problem, so I do need to be able to find this derivative. I cannot math 8 this. I need to be able to find the derivative of something with e, and something with decimals too, which makes it a little bit tougher. You don't need to simplify this, but if you did want to, the negative 0.4 here is basically 4/10. And then if you're good with mental math, or if you are good with a pencil and paper, you could simplify this down to be 6.4 e to the negative 0.4 t. But if you're not comfortable with that, I would encourage you to just leave it exactly like this. And then this is asking us to find the rate at which the coffee is changing when t equals 5. So we want to find what b prime of 5 would be, and that would just involve plugging in 5 into our derivative. So if I were to do the unsimplified version, I'd have 0.4 times 16. The negatives cancel out. And then e to the negative 0.4 times 5. And if you're using the simplified version, 6.4e to the negative 0.4 times 5. And again, you do not need to simplify anything, so you can box up whichever one you're using, and then you are good. The entire difficulty of this problem happens to be just finding the derivative by hand, because this is a no calculator problem. In a lot of the other interpreting rates of change problems, you might have to interpret a rate of change. That can be confusing, maybe a little bit difficult, but just keep your wits about you, know what information you're being given and what information you have to find as well. Remember, if you have a question on the scoring, or if you need to check your answer, you are totally able to do that. And if you have a question that can't be answered by that, feel free to call me over or send me an email, and I'm more than happy to help out.